Morning and welcome back to finally another HyperMu devlog. This will be the first HyperMu devlog that isn't purely about progress. Since the last video, there have been lots of developments, but I'm also starting to discover some of the limitations of my telemetry, limitations of HyperMu's open loop architecture. So I'll be saving the smaller developments for future videos or write-ups and focus today on one of the bigger dynamics questions that I've been tackling in that time. I'll then dive into those limitations a little bit that we've been seeing along the way and wrap up with what might be next for HyperMu. To recap, HyperMu is an open loop telemetry replay multi-body vehicle dynamic simulation written from scratch in Python. Its initial inspiration was to make an extended virtual shaker rig, meaning it had additional modes of exciting the vehicle model, namely by replaying recorded lateral and longitudinal accelerations through the center of mass. For this reason, I sometimes called it a virtual 7+2 post-shaker rig. I rely on static and dynamic correlation to real-world telemetry to validate HyperMu or identify its weaknesses. For this video, I want to emphasize that HyperMu is an open loop telemetry replay simulation, as opposed to other closed loop or free driving simulations. This will help explain some of the design decisions later in the video. In short, HyperMu relies on IMU data gathered during a racing lap and applies those forces to a vehicle model, which predicts all sorts of vehicle dynamics outputs that the users might be interested in. For example, vertical tire load. The vehicle model can then be iterated to improve whatever predicted suspension output the user is interested in. For this devlog, the recently solved dynamics problem I'll focus on is quantifying vertical jacking forces from the available telemetry here. Jacking forces result from two asymmetries in the chassis when cornering. Asymmetric virtual swing arm angles and asymmetric ground plane tire forces. Modeling the asymmetric virtual swing arms in HyperMu was pretty straightforward. HyperMu does not have a full 3D kinematic solver. Instead, key properties which vary with suspension deflection are expressed as basically lookup tables in the chassis definition. And then these tables are interpolated at each step of the simulation. Previously, HyperMu just used a fixed nominal roll center height, but now that we have dynamic virtual swing arm angles, the roll center height is dynamic as well. We'll visualize the changing roll center height and its effects in just a moment. The other asymmetry that is needed to fully resolve the vertical jacking forces is the distribution of the tire ground plane forces, where we have both some known constraints and some necessary simplifications that we have to apply. The combined longitudinal force is estimated from vehicle mass, acceleration, and aero drag, and distributing these forces requires engine torque distribution and brake force distribution, which can be defined in the vehicle specification, but also wheel speed telemetry, tire slip ratio data, which are unavailable to us right now. As a result, HyperMu currently has to assume no ABS intervention, no wheel lockup, and an open differential, at least for now. For lateral forces, the combined value is well known from mass and acceleration, and yaw rate and yaw inertia help estimate the forces per axle. That said, finding the distribution across the axle requires vertical load, which HyperMu is obviously already very good at. We've spent a lot of time in previous devlogs talking about this capability, but it also requires steering angle data, the tire's grip load dependency, and the tire's cornering stiffness, which are also unavailable to us. So generic tire characteristics need to be used here instead. Specifically, I'm using a two-dimensional tire model, meaning that lateral forces are only a function of vertical load, where the grip load dependency is fit to a parabolic curve using known parameters. These simplifications could be critical in closed loop simulations where ground plane forces as outputs are part of the feedback loop, influencing the next iteration's inputs, and the errors start to compound. But HyperMu's open loop telemetry replay approach means that tire ground plane forces are currently only used to find the vertical jack. So the impact of these simplifications are much smaller. I'll talk a little bit more about the implications of these simplifications towards the end of the video. But before that, let's look at some of the unit tests in HyperMu that show the dynamic virtual swing arm angles and the jacking forces in action. Okay, here we go. So HyperMu uses PyTest to structure its unit and integration tests. We have a suite of experiments here, some with synthetic pure lateral or pure longitudinal inputs to get steady state behavior, and others with real world recorded telemetry replay inputs to get, well, real world behavior. In all cases, there are assertions at the end of each experiment which check to see that the simulated outputs are similar to what we expect in the real world. Even if the total magnitude of the jacking effects have errors, these assertions ensure that at a minimum, the direction, the sense of the effects are correct. I've written down some of these real world effects that we expect our virtual vehicle model to emulate. I won't necessarily deep dive into confirming each of these effects in this devlog. There just isn't time for that. But I will say that each of these effects are encoded in at least one assertion downstream in the test suite, and that the test suite completes successfully with a couple of other suites, all as part of HyperMu's Git flow. So that's visible with the passing tag here and a git flow, which calls these test files and executes them um, every time changes are uploaded to my repo. So with all that said, I will run the test file to highlight a couple of the most interesting effects. And we'll do that by calling PyTest and calling the test file. And as always with HyperMu, before launching an experiment, make sure you read the disclaimer to fully understand the limitations of HyperMu before you begin interpreting its results. And we'll go ahead and run the test. So these are the results of the first test case here. The loading function is a synthetic loading function of purely longitudinal acceleration, ramping from 0 to a constant value, in this case, 8/10 of a g. The baseline vehicle has its results represented in orange. The candidate vehicle model has its results represented in blue. And the change to the candidate vehicle model is that the virtual swing arm angle of the rear suspension in longitudinal motion has been increased. You could basically think of this as increasing the anti-squat geometry, although we're not using that nomenclature for these experiments. There's a lot going on here in this visualization, but I'll walk you through it. Just follow the cursor. The first thing that we think of when we think of vertical jacking forces is that the acceleration load paths are being redirected through the suspension arms rather than through the ride springs of the suspension. So accompanying that, we would expect the front axle displacement and the rear axle displacement to be greater, meaning for them to ride higher. In this case, the positive is downwards, so lower values mean that the axles are riding further up. We see that the front axle is riding about 6 millimeters higher on average, and that the rear axle is riding about 15 millimeters higher on average. We also don't expect these kinematics of roll centers and pitch centers and virtual swing arm angles and anti-effects to affect the total tire load on average. Of course, there will be dynamic kind of transient effects and inequalities in the total tire load that'll be induced by these dynamics, but on average, we expect the loading, the total tire load to be the same. And we see that that's absolutely the case here in the lower right-hand corner. We also expect that the active pitch center height will change when we're changing the rear anti-geometry. And here we see that the distributions for the candidate model and the baseline model have basically no overlap, but this is the distribution for the active pitch center at the rear. And the pitch angle itself, as we expect, has also changed significantly. Lastly, the four plots up here, roll angle, for the front and rear axle. They haven't changed very much as we would expect for longitudinal loading, and then the active roll center heights, again, no change there, effectively no change there. So that test case was a synthetic longitudinal loading. So now let's look at a synthetic lateral loading. As before, the baseline configuration is in orange, the candidate configuration is in blue, and the candidate configuration in this case has its virtual swing arm angles increased at the rear axle. Effectively, you could think of this as having a higher kinematic roll center on the rear axle. And the synthetic input that we're using here is a ramp from 0 degrees to 8/10 sorry, from 0 Gs to 8/10 of a G-force, at which point the G-force stays constant at 8/10 of a G. Starting again with axle displacement, the front axle is riding very marginally lower, but the magnitude is almost negligible. The rear axle is riding measurably higher, and even though the magnitude of the mean isn't very much, it doesn't feel like a very large change. Uh, Look at the range from the resting state on the right-hand side through the ramp up until the fully loaded case. We see that the range is more than double for the candidate model versus the baseline model. So proportionally, this is a very significant effect. The total tire load, again, almost identical. It's what we're expecting. So looking at the rolling dynamics now, we see that the active roll center height for the front is basically the same. This is what we expect. And again, the distribution for the active roll center height for the rear has shifted from about 15 millimeters above the ground plane to about 26 millimeters above the ground plane. So there's no overlap in those distributions anymore. And finally, moving on to the roll angles on the left hand side of this chart, as we'd expect, because we now have a shorter roll couple. We have greater roll stiffness on the rear axle. We expect the entire chassis proportionally to roll less, and that's exactly what happens here. The magnitude of roll in the steady state is only about a third for the candidate model what it was in the baseline model. So everything here is behaving as expected. And finally, let's move from a synthetic pure longitudinal or pure lateral loading test case to a test case that uses real world telemetry inputs. The difference between the baseline and the candidate models this time is the same as last time. The rear virtual swing arm angles have been increased on the rear axle. So again, we're thinking of this as having generally a higher rear kinematic roll center. Most of the properties that we expected before are present once again. So the front axle displacement is riding just a touch lower, but the rear axle displacement is riding significantly higher. And in fact, when we look at the maximum upward position of the rear axle, there's a very significant difference from around 15 millimeters downward displacement to 42 millimeters downward displacement. So there's about an inch roughly of difference in vertical displacement from the jacking forces here. Tire load looks as we expect. The active roll center height for the rear axle has shifted very dramatically as we expect. But there is one property here that we weren't expecting, which is that the baseline model has a lower mean magnitude of front and rear roll angles compared to the candidate model. So the expected output here, to reiterate, is that we have greater roll stiffness on the rear axle due to the change in the virtual swing arm angle. So we expect there to be a lower magnitude for the candidate's mean roll motion. This is exactly why we do tests on real world telemetry as well as unit tests with synthetic steady state inputs. My best explanation for the discrepancy that we're seeing here is that as we've stiffened the roll stiffness on the rear axle, it has increased the excitation frequency in roll mode of the entire chassis. And that excitation frequency is now closer to the slalom frequency that we see in this telemetry replay. This telemetry replay was gathered from an autocross course, so it makes sense that there are some slaloming frequencies that might be exciting the chassis more than when it had a lower roll excitation frequency. So that could explain the discrepancy here. But notice also that the standard deviation of the rolling trace is much tighter for the candidate model, which is what we'd expect for a greater roll stiffness as well. So this is why we do unit tests for constant inputs as well as real world effects. We might have transient effects that don't always neatly fit into what our expectations are. But we can also test this with other synthetic inputs, like, for example, lateral G-force frequency sweep that might expose the same behavior. So we see that the vertical jacking forces working in HyperMu are working as expected, but it's still difficult to measure correlation of simulated jacking effects to real world ones, especially since most suspension systems are designed to avoid them. And we've also had to introduce more assumptions and simplifications into HyperMu. But some of these assumptions and simplifications can be removed with expanded telemetry and a more detailed tire data set, which brings us back to our architecture diagram. In short, I think HyperMu has shown at least one limitation here of how far it can go with the current IMU only focused approach. Expanding the input set to include detailed tire data, steering angle, and brake throttle input telemetry would be the best way to improve HyperMu as it is today. But these extra data also enable a full closed loop simulation approach as well, bringing into question whether or not it's worth sticking with the open loop simulation that HyperMu has been using up until now. So lots of opportunities and trade-offs are coming up in HyperMu's future, and I'm still very excited to share everything in devlogs like these. Thank you so much for watching to the end. If you made it all the way here, I'm always looking forward to feedback. I'm always looking forward to comments and critiques. So please let me know if you have any thoughts and have a great day. Thanks for listening. Bye.